Hello, ladies and gentlemen, Mr. Donahue here again. This time we're going to take a look at 5.5b, calorimetry and heat of reaction. So our objective will be to determine heat of reaction, delta H, from calorimetry data. So first off, what is the heat of reaction? Well, the heat of reaction is the heat released per mole of reactant. That's usually what we're interested in, like kilojoules per mole. So delta H is going to be equal to that negative Q divided by the number of moles. Is it positive or negative? Well, think about it conceptually instead of mathematically to avoid some silly errors. Like you might be like, oh, I forgot the negative side. So did the reaction release energy and cause the temperature to go up? If it did, then it lost energy and has a negative delta H. That reaction gave off that energy, so it's a negative change. Whereas, did the reaction absorb energy and cause the temperature to drop? Well, if the reaction absorbed energy, that's a positive change. It gained that energy from the solution and it has a positive delta H. So think about it that way. So here's an example problem. It says a 0.500 gram sample of naphthalene, which is C10H8, is burned in a bomb calorimeter at an initial temperature of 20.00 degrees Celsius. After the reaction, the final temperature of the water is 26.40 degrees Celsius. The heat capacity of the calorimeter has previously been determined to be 420 joules per degree Celsius. Calculate the delta H in kilojoules per mole. Well, first things, to really kind of get going, you want to think, all right, well, they want to get kilojoules per mole. So those are two things I need to get. I need to get the kilojoules and I need to get the moles. So why don't I do the kilojoules first? Well, I know to get the kilojoules, that's going to be my Q. I know for bomb calorimeters, if they give me the heat capacity of the whole system, then that's going to be that capital C times the change in temperature. So that's going to be pretty straightforward. The capital C, they tell me, is at 420 joules per degree Celsius. So I got 420 joules per degree Celsius, and I'm going to times it by the temperature change. Well, it was at 20.00 and went to 26.40, so the change is 6.40 degrees Celsius. When I multiply that across, I get 2688 joules. And if I want kilojoules, I got to divide that by 1,000. So divide that by 1,000, and I get 2.688 kilojoules. So I got my kilojoules, which is the first thing that I need. So I can check that off. I got that. Next thing I need is moles. Well, they tell me I had a 0.500 gram sample, and they tell me what the formula was. So to get moles, I'm going to have to do that whole grams divided by the GFM thing. So I know that I got 0.500 grams divided by the GFM, which is going to be the mass of carbon, which is 12.01 times by 10 because there are 10 carbons, and 8 because I have 8 hydrogens, times by the mass of one hydrogen, which is 1.01, and then I got to add all those together on the bottom. And when I do that, I get 128.18. So the real math is going to be that 0.500 divided by 128.18, which when I do that math, I get 0.00390 moles. So that's the second thing that I need, right? That is the moles. So now I just need to do kilojoules divided by moles. So I'm running out of room, so I'm going to squeeze it in down here. So that's going to be 2.688 kilojoules divided by 0.00390 moles. And I plug and chug, and I get a final answer of 689 kilojoules per mole. And now my last question is that going to be a positive or a negative change? Well, I'm going to think about it this way. The temperature was at 20. It went up to 26.40. So if the temperature went up, that reaction released energy, so it has less energy, which means that it is a negative sign, and that is my final answer, 689 kilojoules per mole. So summarize, tell me, how can you calculate the delta H of a reaction from the calorimetry data? And that's pretty much like the whole thing. That's what this whole video was about. So I hope you found it helpful, and I'll see you in class. Okay, bye.